now that we've been introduced to derivatives of vector valued functions, we want to talk about some properties that flow directly from the definition of the derivative. So if we have r of t and u of t, which are vector valued functions, we have wt, which is some scalar valued function. So its output is a number, not a vector, and some scalar value, then these 7 properties follow directly. The first one is one that you probably would have already thought. Some number times a vector, when you take its derivative, it's the same number times the derivative of the vector. So that's very similar to what you remember from your introduction to calculus, that scalar values can kind of be factored out. The second one is something you probably would have done even if you didn't know know that its property flowed directly, which is if I have 2 vector valued functions that are added or subtracted, then to take the derivative of those together, we can break them apart, take their individual derivatives, and then add those together. So usually what that means is if I have some function, I can break it into individual pieces, take the individual derivatives, and sum them back up. Something, again, you probably would have already done. The third one should be familiar to you. In this case, instead of having 2 scalar functions multiplied together, we have 1 scalar function and 1 vector function. But what we find is that the structure is almost identical to what we expect in a product rule of 2 scalar functions. We take the derivative of the first, multiply the second, and then we add that to the first one times the derivative of the second. So we just perform a product rule as normal, but instead of these being 2 scalar functions, one of them is a vector function. Then we move into sort of the products of vector valued functions. So if I have r of t dotted with u of t, the nice part is that the structure is identical really to the product rule for scalar functions. We have r dot t, but instead of multiplying, it's dotted with u of t, and then we add the first dotted with the derivative of the second. So notice how that structure is almost identical. You know, derivative of the first, dotted with the second, and then you keep the first dotted with the dotted with the derivative of the second. So pretty much identical structure. This one here, so we find it with cross products, it's also the same structure. But instead of using the dot product, we're using the cross product. So products of vector valued functions obey the rules that you might expect them to. Now here's one that also is very similar to your introductory calculus, which is the chain rule. If I have a vector valued function and I sort of represent it in terms of, instead of r of t, it's r of 2t, right? Then when I take the derivative of r of 2t, I take r prime of 2t times the derivative of 2t, which in that case would be 2. So the chain rule works, again, the way you might expect it to. And finally, there's a very important piece here, which may not seem important now, but will as we move on, is that if a vector's magnitude is constant, right? Because r dot dot, that would be the magnitude of r. If the vector's length is constant, then the vector dotted with its own derivative must be 0. So what does that mean? Well, that means that a vector and its derivative are orthogonal if the vector's constant. So if we can construct some sort of constant vector over time, then we can guarantee that that constructed vector, we can always find an orthogonal vector simply by taking its derivative. That's going to come into play a lot, but specifically in the next few sections.